All right, here we are. We're basically just doing the converse of the last video, okay? In the last video, this is the old here. In the last video, we said if two lines are parallel, right? So if we're given that these two lines are parallel, then the implication is they intersect a transversal at the same angle. So these two intersections are the same. So whatever angle this is 20 degrees, then this is a 20, and then we can fill in all the angles. So we got a 160, a 160, 20, and then we have the same thing down here, 160, a 20, and a 160. That's the big idea. So it starts with parallel, leads to angles being the same, okay? In other words, if the lines are parallel, we know all those angle relationships. Corresponding angles are congruent, alternate interior angles congruent, alternate exterior angles congruent, and consecutive interior supplementary. Okay? Today, we're going to look at the converse. So if we encounter two intersections that are the same, now that could be the corresponding angles match. If we encounter a 20 degree and a 20 degree, then we know the lines are parallel, but we actually have more than just the one relationship, right? We have alternate interior, alternate exterior. So if any of those four are true, then that leads us to the lines being parallel. So here we're just switching the order of that converse statement. So if we encounter congruent angles and those corresponding angles, then the lines are parallel, okay? So again, we're really going to try and stick with one assumption and build everything off of that in terms of theorems. So our one assumption is going to be if the angles are the same for corresponding, then the lines are parallel. And then we can prove all the other ones. So this is the like quote unquote obvious truth we all agree to, okay? So if we have two congruent corresponding angles along a transversal, then the two lines must be parallel. So this is the way I think about it, right? Why is this obvious, okay? So I think about it like in one way, right? You're walking along this transversal and you've got your arm out with like a laser gun, right? And your arm's pointing at like a 30-degree angle. So if you keep shooting lasers at this 30-degree angle, right, as you just walk forward, you keep your arm pointed out, all of those lines that you shoot out, all those lasers, right, are going to be the same. Or another way to think about it is, here's a direction, right, that's always going to be the same. Let's call it direction 1. And then you just turn any number of degrees, right? Let's say 20 degrees. Well, that's your new direction, direction 2. So it doesn't matter when you turn 20 degrees. If you just continue in direction 1, you're going in a direction, right? And then you turn right, that same 20 degrees. It doesn't matter when, right? It doesn't matter whether you do it at this street or the next street or whether you're on your bike, right? If you're going in direction 1, which is always the same as direction 1, it is direction 1, and you turn 20 degrees to the right, if you do it here or here, or up here, you're always going to be going in that direction too. You're always going to be going in the same direction. So that's the obvious truth we're saying, right? If you're going along one transversal and you take that right turn of whatever number of degrees, and then later on that transversal you do the same turn, those two lines will always have to be parallel, okay? That's our one assumption, all right? And then there's this tiny little postulate we also say, and what that is that's just saying if we have a line and a point not on the line, we can draw, I mean, you could draw a line through this point in any direction, but the direction we could choose is we could draw a line through that point that is parallel to this line. So that's just an assumption we say. I think we can all agree we can do that, right? Because from that point, we can travel in any direction. So it's just saying you could travel in the direction parallel. And we're going to use that in some of our proofs to add auxiliary lines, okay? Okay, so now with that, I mean, that's two assumptions, but really with this one large assumption, right? If we have congruent angles, then the lines must be parallel. We can go ahead and prove the other relationships, okay? So let's go through and prove them. If you want to skip these proofs and go forward to the homework problems, you can. However, this is really about creating proofs, so this is valuable, okay? So here's the theorem. Again, it's just the converse of one of the last. So instead of the alternate exterior angle theorem, which says if parallel, then alternate interior or exterior angles are congruent. This one is the converse. So it says if the angles are congruent, then we have parallel lines. And so here we're going to start with the assumption that we come across this picture where these alternate exterior angles are congruent, and we want to show that the lines are parallel. To show that they're parallel, all we have is this one way, right? We have our one assumption, our corresponding angles postulate, or actually, to be clear, this is the converse of corresponding angle postulate, right? That would be the name of this one. And so this is the only way we can show lines are parallel so far. So down here, if we want to prove it, that's what we need to do, is we need to show that 2 is the same as 6. Well, we can easily do that. We could say angle 2 is congruent to angle 7. That was given. Okay, and if that was given, then we also know, oh, I should move this up a little as the bottom of the page. Then we go, oh, and you know what? Let's actually take that to the side, because I know that also angle 7 is the same as angle 6, right? Those are congruent. What tells me that? Oh, why, that's the vertical angle theorem. Okay, so now that we have that, we can go ahead and put these together and say, well then, that means angle 2 is the same as angle 6. Again, what's the reasoning there? The transitive property of congruence, because both 6 is the same as 7 and 2 is the same as 7. So if they're both the same as 7, then they're the same as each other. And then finally, if that means if we have corresponding angles are the same, well then the lines must be parallel. So now we know that line A must be parallel to B, and that's by the converse of corresponding angle postulate. Okay, so we have the corresponding angle postulate, which said if parallel, then the corresponding angle is congruent. The converse is the reverse direction. So if we find corresponding angles that are the same, then those two lines are parallel. Okay, so let's do the next one. So converse of the consecutive interior angle theorem. So we start with 4 and 6 are supplementary. So we have 4 and 6 are supplementary. And again, what we want to get is we want to get that corresponding angles are the same. Or we could actually, now that we have this theorem, we could even find alternate exterior angles are congruent. But I'm going to go with corresponding angles. So I want to look for, again, 2 and 6. Okay, so let's start with the given. Okay, so we have angle 4 and angle 6 are supplementary. Okay, that was given. And then over here, we know the relation between 4 and 6. What about 2? Okay, we can't say 2 is the same as 6. That would be assuming the lines are already parallel, and we don't know the lines are parallel. That's what we're trying to prove. That's a question. Okay, so we can't go ahead and say, oh, angle 2 and angle 6 are the same because of corresponding angle postulate. That would be if we knew lines are parallel, but we don't. So what relationship do we know, right? If we don't have parallel lines, the only relationships we know are relationships at a single intersection, okay? And so what relationship do we have? Well, we have between 2 and 4, right? Well, I can say then over here, angle 2 and angle 4 are a linear pair. And I like stating this first. I know sometimes, like on IXL, go straight to that they sum to 180. I like stating this first and saying, well, that's given by the diagram, okay? And then because they're a linear pair, I know that angle 2 and angle 4 are supplementary. Okay, and that was a theorem in our book, I believe. But I'm just going to say we know that because linear pairs are supplementary. Okay, so if we have 2 and 4 are supplementary, and we have 4 and 6 are supplementary, we proved a theorem that was a really simple algebra. Like if you wanted to go to algebra right here and do some quick substitution, it would only save us a few steps. But we proved a theorem that said if 2 angles are supplementary to the same angle, then angle 2 is congruent to angle 6. That was a very misshapen box there. Let's put a smaller box there. And the reason is if 2 angles supplementary to the same angle, then congruent, right? That was the theorem, okay? I can't remember what we called that theorem in this book, but the idea being, right, if angle 4 plus something adds up to 180, and angle 4 plus something adds up to 180, just by simple algebra, angle 2 and angle 6 must be the leftover. right? 180 minus angle 4 on both, so they must be the same as one another, right? And so if angle 2 and angle 6 are the same, so if I know angle 2 and angle 6 are the same, well, those are corresponding angles. So those two angles being the same means A is parallel to B by the converse of the corresponding angle postulate. Okay, let's do another one. So this one's the converse of the alternate interior angle. And I'll just zoom out really quick so you can see that whole proof. So it was a total of 5 steps, right? And you could have absolutely proved this one yourself just by going measure of angle 4 plus measure of angle 6 equals 180, definition of supplementary, measure angle 2 plus measure angle 4 equals 180, definition of supplementary. Oh, and then substitution, measure of angle plus measure of angle equals, and you get rid of the 180. Measure of angle, and then do some subtraction. You get measure angle 2 is the same as measure angle 6. That was subtraction property of equality. And then we would go here to definition of congruent angles. So you could have just reproven that, but we did have that theorem. So if two angles are supplementary to the same angle, then they're congruent to one another. Okay, so let's go to the next one. Converse of alternate interior. So this is going to be pretty similar to the first one, alternate exterior. So we're given that we have a pair of alternate interior angles that are congruent. And what we want to do is show that that means the lines must be parallel. Again, I'm going to base this on corresponding angle postulate, okay, or the converse of it. And so what I want to get is that 2 and 6 are congruent. So I'll start with angle 3 is congruent to angle 6. That was given. And then we also know angle 3 is the same as angle 2. What tells you that? That's the vertical angle theorem. And look, if these are both the same as angle 3, well, then they're the same as each other. So we have angle 2 is congruent to angle 6. And that's by the transitive. You don't have substitution, remember. There's no substitution for geometric objects. But we do have the transitive property of congruence. So if they're exactly congruent to the same thing, they're congruent to one another. Well, now, if angle 2 and angle 6 are the same, that was our very first assumption, right? That means that A is parallel to B. And again, that's by the converse of the corresponding angle postulate. Okay. Last one, this is a little different. It's saying if two lines are perpendicular to the same line, then parallel. So let's start with A being perpendicular to B and C being perpendicular to B. So they're both perpendicular to B, okay? So let's go ahead and start. Well, we have A is perpendicular to B, okay? Oh, sorry, I drew an arrow. I meant to write given. Okay, and we also have C is perpendicular to B, okay, and that was given. All right, so what does perpendicular mean, right? Perpendicular means two lines form or meet to form a right angle or meet to form a 90-degree angle. So I'm going to go ahead and say this means A and B are perpendicular, means that angle 2, so angle 2 is a right angle. Okay? And, oh, and that's the very definition of perpendicular lines. Okay, and so this goes to same thing, except I'm going to do angle 6. So angle 6 is a right angle. And that's definition of this. Again, anytime you start with a symbol or a word like perpendicular, the only way to get somewhere from there is to use the very definition of it. So that's the very definition of perpendicular lines. Okay, so now that we have two right angles, we could either use our theorem that says all right angles are congruent and just go angle 2 is congruent to angle 6. And that was our theorem that said all right angles congruent, right? I think that's the most elegant. Or what you could do is you could get rid of that and you could do it yourself. Okay, so let's just get rid of that. We could also just go, well, that means that the measure of angle 2 is 90 degrees. That's the definition of a right angle. We could say same thing, measure of angle 6 equals 90 degrees, definition of right angle. Oh, let's just leave this. I was going to go back to the other one because it's more elegant, but why not show all of it, okay? Well, both of those angles are equal to 90. Well, then they're equal to each other, right? So we're not waving hands here and being like, I can't finish those last two steps. I'm really uncertain. We're working out these mental muscles. We're trying to come up with every single micro step here, okay? Comfortable with all of it. Okay, so this could either be transitive property of equality, which is what I'll choose, or it could have been substitution also. So transitive property of equality, and then that tells me that angle 2 is congruent to angle 6, because if two angles have the same measure, then they're congruent. That's the very definition of congruent angles. And then lastly, if we have those corresponding angles matched, just like the other proofs, that's what we were looking at, well then we know, in this case it wasn't A and B, it was there A is parallel to C. Just looking at the picture, those are the two lines here, right, A and C. And so we know those are parallel again by the converse of the corresponding angle postulate, okay? So, big picture, what do we have? I'm just going to zoom out here. The big picture is we have 4 biconditionals, okay? The 4 biconditionals are corresponding angles congruent, if and only if parallel. So you can go either direction. Parallel lines means the angles are the same, or angles the same means, or angles the same means the lines are parallel, right? So all of these now are biconditionals, and I'm okay with you using that on a proof. Okay, same thing with the alternate interior. Parallel lines, angles are congruent, or if angles are congruent, the lines are parallel, and that's true for all 4 of our sets, okay? All right, that's the big picture for this entire last 2 sections of video. All right, so here's a big common mistake, okay? It shows up in 2 different ways. What if we have 2 sets of parallel lines, okay? People just start waving their hands and being like, everything's parallel to everything. Okay, so let's be clear. If we have angle 2 is congruent to angle 3, then which lines are parallel? We do not have 2 sets of parallel lines, okay? Then, oh, and I guess I should label these A, B, C, D. Okay, so let's think about it. If 2 is the same as 3, 2 is the same as 3, these are corresponding angles. These are corresponding angles along this transversal. So then B is transversal, right? And what are the 2 parallel lines? Then C is parallel to D. Okay, the common mistake is we know nothing about A and B. Right? That's the common mistake, is people accidentally overstate what they know or accidentally say A is parallel to B, right? But we know nothing about an angle at A. So how would we know anything? A could be going like this. A could be going like this. We know nothing about A. We only have these angles that lock B, C, and D together. And then all you need to know is which one is the transversal that's hitting the other 2 lines, right? C is never hitting D, but B crosses both of them. Another way to think about it is this intersection and this intersection always lie across the one transversal. So all you have to do is say the 2 angles are on what line? That's the transversal, right? Okay, so let's look at the other one. This is really common when we get to quadrilaterals. So we'll get that these 2 angles are congruent. So in this picture, if angle 1 is congruent to angle 2, then, okay, so what do we know? What do we know? Again, this is the transversal from this intersection to this intersection. They have to lie on the same transversal. So I draw this line across and I go, okay, so here's the transversal. So what 2 lines is that transversal hitting? Well, you can say like, well, it's hitting this line, but that's not the angle we're talking about. We're not talking about this angle between this line and transversal. No, we're talking about angle 2, which is between what, right? Angle 2 is between, so erase that. Angle 2 is between this line. Oh, I guess I should label the sides like A, B, C, D. Okay, so angle 2, let's just write it. Angle 1 is between A and transversal. Angle 2 is between what, right? Like when I say between, I mean the sides of the angle are literally, right? Angle 2 sides are B and the transversal. And so what we're saying is from the transversal, if we shoot out in the B direction, and from the transversal, if we shoot out in the A direction, those are the same. Well, then that means A is parallel to B, right? And again, we know nothing about C being parallel to D, right? That's the mistake, is we know nothing about this side and this side from that one pair. That one angle being the same along this transversal. And then that one angle over here just tells you in what direction side B and side A shoot out at from the transversal. We know nothing about C. This point could be way higher and C could be like this. It could be even higher and C could be like this. We know nothing about that side C, so we don't know whether it's parallel to D. So a common mistake is when we have two sets of lines, kids just waving their hands and saying everything's parallel. So really take time to look at why, right? The two angles along one transversal, what two other lines off the transversal are they dictating the direction of? And then now we can say, oh, well, then that means only these two lines are parallel, okay? All right, so let's just do a bunch of homework problems. So 5 different methods to prove that two lines are parallel. Well, even if we just go more generally, right? 1, we could even say that the same slope, right? Like if we're in the coordinate plane. 2, we could say if corresponding angles are congruent. 3, if alternate interior angles are congruent. 4, if alternate exterior angles are congruent. 5, if consecutive interior angles are supplementary. What else? 6, we have if both lines perpendicular to same line. Right, so if any of those are true, I added the same slope one. If any of those are true, then we know the lines are parallel. So those are kind of our bread and butter of how to prove it. Honestly, the ones you're going to use the most are these first 3 in different circumstances. This one up here when you're on a coordinate plane, and then 2 and 3 in pretty much every other circumstance are going to be your most common, okay? All right, so find a counterexample for the following statement. If lines L and M are cut by a transversal, so that consecutive interior angles are congruent. So consecutive interior angles are supposed to be supplementary to have that 180 degree turn to say, well, I made a turn here and a turn here, and in total I'm going back exactly the same direction as I came, just facing the other direction, right? So I made a 180 degree turn. But instead, this says the angles are congruent. And so it says, well then, these two lines are parallel, which isn't necessarily true if these are congruent, and T is perpendicular. So what they're doing is saying, if we assume they're supplementary and congruent, well, they're saying then it must look like this. So they're assuming that they're already 180. Then they state they're congruent. So the only way for 180s to be congruent is if you cut it in 2 and you get a 90 and a 90. And so this is the case they're kind of envisioning. However, all they said was congruent. They never said anything about the 180. So here's another pair of congruent angles, right? This angle is congruent to this angle. Here's line L, here's line M. And those two are definitely not parallel, right? I can literally show them intersecting right here, right? So there's L and M that are cut by a transversal. T, it even has a name. So here's transversal T. Right, so that consecutive interior angles are congruent. Here's consecutive interior angles are congruent. I'll highlight them in pink. Right, here's a congruent angle to a congruent angle. That's the consecutive interior angles from L to M. But the two lines are not parallel, and T is not perpendicular to either line. Okay, let's do this. So given the following information, determine which lines. Oh, so this is really that common mistake thing, right? So we're going to be really careful. So it says 16 is the same as 3. So if this angle is the same as this one, those are corresponding angles along this transversal, which means we are shooting out two lines that are parallel. Pachoo! Pachoo! These are the two that are parallel off of that transversal. So we know for 4, it's L is parallel to M. Okay, so the next one, 4 and 13. So 4 and 13... there and there. So these are alternate interior angles. Again, connecting these two intersections, here's the transversal. So what are the two laser beams we're shooting off in the same direction? Pachoo! Pachoo! Here's our two lasers. So again, that's L is perpendicular to M. In this case, it says state the theorem postulate. So for this first one, it was the converse of corresponding angle postulate. Sorry, I didn't see the second half that says state. And then L is perpendicular to M. In this case, it's the alternate interior. So it's the converse of alternate interior angle theorem. Okay, let's look at the next one. So the next one says 14 and 10 add up to 180. So let's check. So 14 and 10 add up to 180. So that means we're coming down and we make a 180-degree turn this way. So I can already visualize which two lines are parallel, but let's just connect these. So here's my transversal, and then we're shooting off two things in the same direction. We're going pachoo and pachoo. And so these two is P is parallel to Q, and that was the converse of the consecutive interior angle theorem. Okay, 1 and 7 are the same, so let's get out of here. Okay, so 1 and 7, so this one and this one. So connecting these two intersections, here's our transversal. Okay, and then what do we shoot out from there? We shot out pachoo and pachoo to form this angle and this angle. And those are alternate exterior angles are congruent, so we do know P is parallel to Q, and that's by the converse of alt ext angle theorem. Perfect. Okay, so just really clearly choosing which of those four lines are parallel, if any. Okay, this one's a kind of funky way to word, right? So it's saying find x so that L's parallel. And kind of like it's mentally like kind of a backwards thing, right? So you're like, wait, do I assume they're parallel? And kind of yes. So we have essentially two things, right? You're saying like if x equals something, then angles are the same. And then you go, if angles are the same, then parallel. So this is kind of the chain law syllogism logic. And so what we're trying to do is say, what x do we put in here? And so we are going to say, well, I want to work backwards and say, what x do I need? That would then work to say, well, then the angles are the same, and then the lines are parallel. So we do kind of, we don't actually assume they're parallel, but we do use like, okay, if they were parallel, like hypothetically, what would that result in x being? And then we can put it in here because it is a biconditional, right? And so we're saying, okay, well, for these angles to be the same, right? These are corresponding angles to be the same. Well, then I know that 14x plus 9 would be the same as 5x plus 90. And so if that's true and I need to solve for x here, then that means the entire angles are the same, right? That was literally the equation I have written here. And then the corresponding angles being the same would then mean the two lines are parallel. So all I need to do is solve this now. So subtracting 5x from both sides, and then subtracting the 9, we get 9x equals 81. We get x equals 9. So if x is 9, then the angles are the same. So let's just check. We plug in 9. That's 90 and 36. So that's 126 plus 9. That's 135. Over here, 9 times 5 is 45. Plus 90, that's 135. So if x is 9, we get two angles that match. And if corresponding angles are the same, then lines are parallel. So again, I understand if that could be confusing for you, but again, just know that it's a biconditional. It is. If the angles are the same, then parallel. If parallel, then angles are the same. Okay? So let's go to this next one. So this is saying what's the relationship between this angle and this angle. And you're like, what the heck? Those aren't a named angle pair. What the heck? Well, a couple ways you could deal with this. You could say, we want to get that these lines are parallel, so we want to have this angle right here be the same, right? Because if corresponding angles are the same, then we have the lines parallel. And so what would make that be the same? 7x, well, that would be if 9x minus 5 plus 7x plus 3, if these two angles add up to 180 degrees, right? Because the corresponding angles need to be the same, so we can put the angle down here, and so now we just need these two to add up to 180. So if that's right, and so let's just check and see if that works. So we add them together, we get 16x minus 2 is 180. We add the 2, so we get 16x is 182. We get then 10 of those plus 22. That doesn't work out evenly. Did I do something wrong? 9x minus 5 plus 7x plus 3, that's 16, that's minus 2. Okay, so we divide, we get x equals 180 divided by 16, divided by 2, we get 90 over 8. That's 182. We added the 2, so that's 91 over 8. Bummer, I do not like that this doesn't work out nicely, because that's going to make plugging it in much harder. But okay, there's nothing else that goes in, because the top isn't even, and this is made of just 2's. So 91/8, really? I'm going to just pause and use a calculator to double check that really quick. All right, I just plugged it in calculator. We got 97.375, 82.628, and yeah, those do add up to 180. So the 91/8 here, or 11.375, was the value of x there. Okay, so now given the following information, determine which lines are parallel, if any, and then state the theorem or reason. So you might come across ones where you say no, and these are a lot of craziness. And after that, we're just going to do a bunch of proofs, okay? So again, the lesson is over, but now we're just applying it and using it, okay? So given the information, determine, okay, so 2 and 8. So 2 and 8 are alternate interior angles across this transversal, just connecting the two intersections. And so that's dictating that A and B are parallel. That's converse of alt int angle theorem. Okay, let's erase that. All right, the next one, 9 and 16. So 9 and 16 are congruent. So that's not telling us anything here. Okay, now if it was saying 9 and 13, we would know lines are parallel. But these don't have a relationship here, right? Remember, we've only got those few ways: alternate interior, alternate exterior, or corresponding. If any of those three are congruent, we know parallel. And the other one's consecutive interior angles are supplementary. But this is talking about congruence. So this is nothing. Okay, 2 and 10. Let's check 2 and 10. So 2 and 10 are just corresponding angles. Here's that transversal that connects them. And then here are the two lines that shoot out. So that tells us L is parallel to M by converse of the corresponding angle postulate. And then 6 and 15. Okay, let's switch colors here. 6 and 15. So 6 and 15. Again, that's not telling us anything. If those were supplementary, that would be close to, and we could use that to show consecutive interior angles are supplementary too, which actually be a kind of fun proof there. But no, this doesn't tell us anything. That's not one of our 4 that we know. Okay, let's look at the next one. Angle AEF, so that's here, is the same as BFG, so BFG. So those are corresponding angles along this transversal. And so what sides does that shoot out? That shoots out this ray and this ray. And so we would know that lines AE is parallel to line, and it doesn't matter which BD or F you use. I'm going to use DF for no reason. And that would be by the converse of the corresponding angle postulate. Okay, let's look at the next one. We've got angle AEB, EAB. So we've got this angle here. And then we got, that's the same as DBC, so DBC. Oh, again, this is just the corresponding angles along this transversal. And so what lines are they shooting out? They're shooting out this line, and they're shooting out this line. And so that's going to be line AE. Actually, it's the same exact answer as the last one. I'm going to just use the same name even as DF again, and that's by the converse of the corresponding angle postulate. Okay, let's look at the next one. We got EFB, so E to F to B, this one, is the same as CBF, so CBF, this one. Oh, so now we got alternate interior angles along this transversal. And so what are the two rays we're shooting out here? We're shooting out this one, and we're shooting out this one. So that tells us that line EF is parallel to line BC. And that's by the converse of the alternate interior angle theorem. And the last one, it's telling us that the measures add up to 180, or in other words, the angles are supplementary. So we're hoping this is a consecutive interior angle thing. So let's go ahead and do this in pink here, GFD. so G to F to D, so this angle here, and CBD. So CBD, these two add up to 180, so we got that 180-degree turn here. And again, this transversal connects the two intersections, which means we're talking about this and this as the two lines. And so that tells us that we've got line CB is parallel to line GF, and that's by the converse of the consecutive angle theorem. Okay, so we're going to jump to 21 here. I got to pause this to jump back to Zoom. I'll come back. We'll do these last 4 problems, and then we'll do, I think I did 4 proofs. We'll jump over to IXL. So we got lots of practice here that we're going to do, okay? All right, we're back. So again, this one's talking about what lines we know to be parallel given this stuff. So if any. So let's go in here. Let's see, HLK, that's this angle, is congruent to JML. That's corresponding angles along this transversal. So that tells us that this line and this line are parallel. So LH is parallel to, let's say QT. Let's name it by the bottom for no reason at all. And that's by the converse of the corresponding angle postulate, okay? Next one, we've got the two angles PLQ. So P to L to Q, so that's this angle, is the same as MQL, so M to Q to L. So those are alternate interior angles along this transversal. And so again, this is where people get confused. You've got that four-sided figure in the middle. But off of that transversal, we're launching this line, and then we're launching this line. So the sides of those angles form. And so that tells us the same lines are parallel. I'm going to name them differently. I'm going to call this one LP this time. And the other one, I'm going to call it QM this time. But really, they're the same line. We're just using 2 different points on the line to name them. And this one's the converse of the alternate interior angle theorem. Whoa, I put an extra L there in alternate. Okay, now we've got supplementary angles here. So we're hoping they're consecutive interior, because otherwise we kind of got nothing. So we got PLQ. So PLQ, that's the same one. Oh, sorry, I was looking at the last problem. Of course, it's the same as the last problem. MLP. So we've got M to L to P. So this angle is supplementary with RPL. So R to P to L, supplementary with this one. So that means we got a 180-degree turn here. That I already know which lines are parallel, but let's just see. So here's our transversal. That's launching off this line and this line at a total of 180 degrees between them, meaning we got this straight parallel line. So we've got MN is parallel to QR, and that's the converse of the consecutive interior angle theorem. And last one, we got perpendiculars here. So I'm guessing it's 2 lines that are perpendicular to the same. So look at this, perpendicular PR, perpendicular PR. Well, if they're perpendicular to the same line, then they're parallel to each other, at least in 2D space. In 3D space, that's not true. What? Think about the example there. Oh, I could show you with my hands, but we're not in person. Okay, anyways, so if these 2 lines in this diagram, this 2D space, are perpendicular to the same line, I don't even need the picture. I know HS is parallel to JT. That was one of our theorems we did up top. I don't know a name for it, so I'm going to just say 2 lines perpendicular to same line, then parallel, right? So I can always just write out the reasoning of the theorem, and we already proved it, so we could refer back up to it. So now let's just do some proofs, okay? So here we're given angle 2 is the same as angle 1. And we're given angle 1 is the same as angle 3. So eventually we could get all 3 of those are the same. And we want to get that this line is parallel to this line. So the only way to get the lines are parallel is either same slopes or our postulate and theorems from this section saying if like parallel, if corresponding angles congruent and so on. So let's see what we've got here, okay? Well, the only like angle pair here that shares a single transversal are 2 and 3, right? Because 1 lies on this transversal, and we know nothing about this bottom intersection. So we're not going to use 1 in terms of our penultimate second to last step. So really what we're looking for here is, can we get angle 2 is the same as angle 3? Because those are alternate interior angles along the same transversal. that would tell us that the lines they launch off the transversal are parallel. So what we need to do is start with angle 2 is congruent to angle 1. That's given. Okay, and then I'm going to slide this to the side, and we're going to do the same thing over here with angle 1 is congruent to angle 3. And you probably, when you saw the two givens, you already thought, well, I could combine those, right? Because you guys are experienced geometrateurs. Yeah, you can just make up words. Okay, so we go angle 2 is congruent to angle 3. And so that we just combined. They were both equal, or I mean congruent to angle 1, so they're congruent to each other. So that was the transitive property of congruence, okay? So now that 2 is the same as 3, they are alternate interior angles. Now, if you wanted to be really clear, you could say like angle 3 and angle 2 are alternate interior angles of these two lines and this transversal, and that would be given by the diagram. But we're just going on the assumption that the person reading your proof knows enough geometry to read a diagram, and so they're looking at the diagram and they see that 2 is the same as 3, and then you say, well, then I know that, and we're going to word it exactly the same as up here. So they're saying segment ST is parallel to segment UV, and we know that by the converse of the alternate interior angle theorem. Okay, or you could say the alternate interior angle biconditional. Okay, now let's go down here. Okay, we're given AD is perpendicular to CD. So AD, CD, so that's a right angle shown in the picture. 1 and 2 are the same, got it. We want to show that BC is perpendicular to CD. We want to show that this is a perpendicular line. Oh, geez, how are we going to do that? Well, the only way to show that's 90, right, is some form of other angle relationship leading to that. Now, if we can show it's the same as the other angle, that's great. Or we could show it's supplementary to a 90-degree angle, and then that would be 180 minus 90 is 90 left over. So I think the way we should start is by using this relationship of 1 and 2. What does angle 1 and 2 being congruent tell us? Well, we just did that same thing up here. If we have angle 2 and angle 3 are congruent alternate interior angles, they show that those lines are parallel. So notice if I erase this, right, what we've got here is this transversal going across with angle 2 and angle 1 congruent. Well, that launches off two parallel lines. That launches off this line and this line parallel. So let's start with that. So let's start, well, we know angle 1 is congruent to angle 2. That was given. And that actually tells us that line BC is, or we can go segment, doesn't matter, is parallel to segment AD. Okay, that was the converse of alternate interior angle theorem. Okay, so now we could use that. Okay, so now that we have those lines are parallel, that was helpful. Okay, how could we use that? So we've got this is parallel to this, and this is a right angle. So let's pull in the right angle, okay? Let's go with consecutive interior angles. So if this is a 180-degree turn, right? And that's 90 degrees. Then we've got another 90 degrees. Or we could do, we have a shortcut theorem that takes us there. But let's just do it ourselves manually rather than using the shortcut theorem this time. So let's go ahead and say, well then, angle BCA, or in this picture it's unambiguous. We can just call it angle C. And angle, and this one's not ambiguous, or would be ambiguous if we called it angle D, because there's more than one angle there. So let's say angle CDA, and we can say R supplementary. That's the forward, so not the converse, of the consecutive interior angle theorem. Okay, and then over at the side, let's say, well, and we also know that, well, we don't know it's a right angle yet, so let's start even before that. Let's say, well, we know AD is perpendicular to CD. Okay, that was given. And then that would tell us that angle ADC, well, or CDA, we wrote another one, is right angle. That's definition of perpendicular lines. And then we could go to algebra with both of these. We could say, oh, well, then that means measure of angle ADC is 90 degrees. Okay, and that's the very definition of a right angle. And over here we can say, well, the definition of supplementary is that the measure of angle C plus the measure of angle, I'm going to switch the order at ADC so they both match, they're in the same order, equals 180 degrees. And that was the definition of supplementary angles. Okay, well now I could substitute that in. So if we substitute that in, we get that the measure of angle C plus the 90 degrees that we substituted in is 180. Okay, that was substitution property of equality. And then we could say, well, we could just subtract, and we could get the measure of angle C is 90 degrees. And then we're going to go from there to angle C is right angle. And then we're going to go from there to the thing we wanted, which is BC is perpendicular to CD. So BC is perpendicular to CD. So we had a shortcut proof we could have used in here, but I like actually, exercising our proof muscles. So it's okay to do it all. So the way we got to is 90 is we subtracted 90 from both sides. So that was the subtraction property of equality. Okay, and then the way we got from 90 degrees to right angle is the definition of a right angle. And then the way we got from a right angle to perpendicular was the definition of perpendicular lines. Whew, that was good. We could have done that shorter, but I like that. That was a nice, elegant little proof there. Okay, let's go on to the next one. So we know that JM is parallel to KN. Okay, so that's going to tell us some angles are congruent. And then we know 1's the same as 2 and 3's the same as 4. We want to get KM is parallel to LM. So really, the way I see it, of all the numbered angles here, if we want to show these two lines are parallel, there's only two transversals. There's this transversal, but I don't see any angles labeled here and labeled here that we could match. Or there's this transversal, and we do see an angle here and an angle here that should match, right? 3 doesn't relate because it's on a different transversal, so we don't care about angle 3. But angle 2 and angle 4, if we could get those the same, that's corresponding angles the same, that means those two lines are parallel. So I think our penultimate step here is going to be, and I'm going to write it in, angle 2 is congruent to angle 4. We don't know how we're going to get there, but then from there we could say, oh yeah, well then KM is congruent to LN, and that would be by the converse corresponding angle postulate, right? So that's where we probably want to finish. We want to get 2 is the same as 4. Okay, well we already know 1's the same as 2 and 3 is the same as 4. Could we get any link between these? Like maybe 2 is the same as 3? So is 2 the same as 3? I don't know. How could we get this? Oh, look at this though. We could get 1 is the same as 3. Look at that. How could we get that? Well, we have parallel lines, and we have corresponding angles 1 and 3. So let's go up to the top. We'll start with JM is parallel to KN. Okay, and that was given. And then from there, we then know corresponding angles must match. So angle 1 is congruent to angle 3. That's the corresponding angle postulate. Okay, and then we're going to bring in the other pieces and we're going to start like substituting or doing transitive property. Okay, I'm going to move that down. So we want to get 2 is the same as 4. So what we're going to do then is let's bring in one piece at a time. So I'm going to move this over just so I have a little room. Okay, so I'm going to say, well, 1's the same as 3, but also angle 4 is the same as angle 3. Okay, that was given to us. So we could combine these now and we could say, well, if they're both the same as 3, well, then angle 4 or angle 1 is the same as angle 4, right? That's the very transitive property of equality, of congruence. Oof, caught myself there. Well, we have 1's the same as 4. We want 2 is the same as 4. But again, we have that other given, right? So we go, oh, well, we also know angle 1 is the same as angle 2. Again, that was another given. So notice I pulled in the 3 givens in separate times, and it was I only pulled them in as I needed them. So now these two go together, and we get angle 1's the same as angle 4. So I'm just going to go ahead and pull. I knew this was going to be the end of our proof, so I pull it in now. And I say, well, angle 2 is the same as angle 4 because they were both the same as angle 1, right? So if they were both the same as this angle 1 here, well, then that's the very transitive property of congruence. And there we go. So we started with a parallel line, and we actually had to prove a different set of parallel lines there. Oh, that was a fun proof. Okay, so one more proof together, and then we'll maybe jump on IXL for a couple proofs. So we got RSP. Okay, let's look at this. RSP, the whole angle, is the same as PQR, the whole angle. And then we know QRS, so that's this angle right here, and PQR are supplementary, so that's this whole angle. Okay, so we know QRS. So we know those two are supplementary, which will tell us that we've got some parallel lines here. Oh, this is a cool proof. I'm seeing what's happening here. So if we have those two angles are supplementary, that means this is a 180-degree turn. So that means we could get then that these two lines are parallel. We can't get the other ones. That's a common mistake. People jump to that. But a 180-degree turn here only tells us the top and bottom sides are parallel. Then what we're going to need to do is use that. We'll say, okay, well, how could we use that? I'm just developing this, just sketching it out in our brains. So we're going to really get that these are parallel first. That's going to be like our first steps. Might take 2, 3, 4, but that's going to be our first goal. And then after that, we could say, well, if those are congruent, then we could say our next step could be alternate interior angles congruent. So this piece matches this piece. That could be like our step 2. And then if we have the bigger angles are congruent, what we're going to have to do is that segment addition, which I know it gets a little tedious, right? And so then step 3 would be some sort of like segment addition postulate and subtraction to get that these angles match, right? So these two match. And if we get these two matching, then that would tell us that the lines here and here are parallel. Okay, that would be our fourth step. All right, so we got a plan. All right, let's do it. Let's start with angle QRS and angle PQR are supplementary. Whoa, are supplementary. Okay, so that right away tells us those are consecutive interior angles, supplementary. So that tells us that RS is parallel to QP. Okay, that's the converse of consecutive interior angle theorem. Okay, and then that angle relationship tells us, that's where we were going to number 2 here, is then we wanted to be able to say, okay, well then we know that angle RSQ is congruent to angle RSQ is congruent to SQP. Okay, and that was alternate interior angles congruent. So alternate interior angle theorem. Okay, so I'm going to put this off to the side. So we've got that. Okay, we got those two angles. And now we need to do some segment addition here to get this other piece. So let's state the segment addition postulate. We'll have to do it twice, which is a little frustrating that we have to do it twice. So I'll do it in green. Okay, so we're going to say that angle, so the measure of angle, where do I want to do this? Organization. I could zoom in a little so I can write smaller. So let's say the measure of angle RSQ plus the measure of angle PSQ equals the whole angle, the measure of angle RSP. Okay, that's the segment addition postulate. And then we also separately, so I'm actually going to rearrange my proof a little bit, okay? I'm going to take the IXL proofs part, just erase it. I'm going to move this down below, and I'm going to shrink it. You know, I could do that. What? That's so cool. And I'm going to move it down here for later. Okay, so I'm going to move this over to here. I'm going to shrink it a little bit too, and we're going to zoom back in. Okay, so we got this. I'm going to do the same thing in green for the other angle. I'm going to say the measure of angle RQS plus the measure of angle PQS is equal to the total measure of angle RQP, so the bottom angle, that adds up. Okay, so that was also the segment addition postulate. Well, I'm going to go ahead and just link these together, right? Because we're given that RSP and PQR, big angles, are the same. So I'm going to go ahead and right in the middle of these two, I'm going to put this off to one side. I'm going to put this off to the other side. I'll shrink it a little bit because I write so huge. And then right down the middle, I'm going to say, well, I know the given was angle RSP is congruent to angle PQR. And that was given. And so if it's given that those two are the same, well then I know that their measures are the same. So measure of angle RSP equals the measure of angle PQR. Okay, that's the definition of congruent segments. Okay, and then I'm going to substitute those in, right? I'm going to substitute in this, right? I'm going to put this over here. I'm not going to have that arrow in my flowchart, but I'm just showing you. And then this measure of PQR, I'm going to put this in here. So I'm going to take the bigger expressions and substitute those in. Okay, so I'm going to erase those pink marks so they don't mess up my flowchart. Okay, so putting these three together, I'll extend this one. Okay, so what that does is that gives me that measure of angle RSQ plus measure of angle PSQ equals measure of angle RQS plus measure of angle PQS. Okay, so that's all added together, and that was substitution property of equality. Okay, so now what we want to do is essentially just take those equal values that we have down here and subtract them from both sides. So let's extend this part of the proof to the measure of angle RSQ is equal to the measure of angle SQP. Right, that's the very definition of congruent angles. All right, so now I'm going to take this. I'm going to slide it up. It's a little funky that we did two separate proofs here, but when these two combine, we get, okay, well, I can now use this and say, all right. And remember, the subtraction property of equality says you can subtract the same thing from both sides, but it doesn't have to literally be the same letters. Since RSQ and SQP have the same measure, I can subtract the measure of angle PQS from the right and the measure of angle RSQ from the left, and the subtraction property of equality, whoa, my keyboard jumped up. I can do that from the two sides because they're the same number. So it doesn't matter what letters are hiding the numerical value, you can always subtract the same number from both sides, and that's the subtraction property of equality. I'm just subtracting the same number, right? It doesn't matter whether I call x on the left and y on the right. If x and y are both 6, I can subtract 6 from both sides. And so now we're left with just the rest. So PSQ, so the measure of angle PSQ is equal to, and then RQS, so the measure of angle RQS on the right. Okay, let's look what we're trying to prove again. So we're trying to prove those lines are parallel. Well, now we've got I'm going to erase this stuff on the picture now that we've used our plan here. Okay, so what we've got now is that this angle is the same as this angle. So those are along this transversal, and they're shooting off the line. This line is the other side of the angle, and this line is the other side of the angle. So that's telling me exactly what we want. PS is parallel to RQ, and that's because alternate interior angles are congruent. So all we need to do here is say, oh, well then, we have the actual angles are congruent, not just their measures. So the angles are the same, RQS. That was definition of congruent angles. And then finally, that would tell us the lines are parallel, and that's by the converse of alt int angle theorem. What a cool ass proof. Okay, so just PSQR, just to match the order. So PS is parallel to QR. There we go. All right, guys, hope you enjoyed that. I'm going to just jump over to IXL for a few minutes just so you can see some of the terms they use. But that was, a couple proofs. So I was going to do IXL proofs, but it's a little clunky just to follow the IXL. You can go on to D6 and D7 in geometry, proofs involving parallel lines, both 1 and 2. And I think they're great practice for you. They immediately tell you right or wrong. their terminology is almost the exact same as what we've been using. I really encourage you to go there and practice, but it was kind of clunky for me to do it and you to follow. All right, you guys, enjoy.